The second component of the EVM architecture is memory. As was just mentioned, memory in EVM is volatile. This means that data placed in memory is not persistent across transactions on the blockchain. Memory in EVM is linear, it's a byte array, and therefore addressable at a byte level. It's also zero initialized. And there are three specific instructions that operate with memory. There is mload, which loads a word from memory and puts it onto the stack. There is mstore, which stores a word in memory from the stack. And there is mstore8, which stores a single byte in memory from the stack. The next component of the EVM architecture is storage. Unlike memory, storage in EVM is non-volatile. This means that data put in storage is persistent across transactions on the blockchain. And in EVM, storage is implemented as a key value store between 256-bit keys and 256-bit values. Storage is also zero initialized. Now, to understand how storage fits in within the concept of accounts and the blocks on the blockchain, recall that every account has a storage root field. This storage root field, implemented as a modified Merkle-Patricia tree, captures all the storage associated with that account. This is really relevant for contract accounts that have associated storage. And these storage roots within the accounts are further captured as part of the state root, which is one of the fields in the block header that we discussed. There are two instructions that operate specifically on storage. There is sload, which loads a word from the storage and puts it onto the stack. And there is store, which stores a word from the stack and puts it into storage. The final component of the EVM architecture is what is known as call data. This is used specifically for data parameters of transactions and message calls. And this is read-only, it cannot be written to, and it's also byte addressable. And EVM has three specific instructions that operate with call data. There's call data size, which gives the size of the supplied call data and puts it onto the stack. There's call data load, which loads the call data supplied onto the stack. And there's call data copy that copies the supplied call data to a specific region of memory. Computer architectures are typically classified into either von Neumann architecture or Harvard architecture, and this really depends on how code and data is handled within the architecture. Are they stored together? Are they transported over the buses together? How are they cached? And so on. In the case of the EVM code is stored separately in a virtual ROM, and there is a special instruction to access the EVM code. This is an interesting fact to know about the EVM architecture. And another concept typically associated with architectures is the concept of ordering. Big endian ordering versus little endian ordering. In the case of the EVM, it uses the big endian ordering. And what this means is that the most significant byte of a word is stored at the smallest memory address, and the least significant byte is stored at the largest address. Now let's take a look at the instruction set supported by EVM. All the instructions supported by the EVM can be categorized into 11 categories. There is the stop and arithmetic operations. There is the comparison and bitwise logic. There's SHA-3 instruction. There's environmental information, block information, stack memory storage and flow operations, push operations, duplication, exchange, all these operate on the stack. Then we have logging instructions, and then finally we have the system operations. Now let's take a look at each one of these categories and see what instructions they contain. Stop and arithmetic instructions. The format for each of these instructions that you see on the slide are in the form of the opcode that you see, in the form of the hex representation, 0x00 for stop, and then stop itself is referred to as a mnemonic. And then the two numbers that you see after the mnemonic refer to the number of stack items placed for this instruction and the number of stack items removed. So in the case of stop, the opcode is 0x00. So it's really the first instruction in the instruction set mapping. The mnemonic is stop, makes sense. And 0 items are placed and 0 items are removed from the stack. Add has 2 items placed onto the stack, the 2 operands. The computed result, the addition, is placed back onto the stack. That's why you see that there is 1 item placed onto the stack, which is the result, the addition of the 2 inputs. The same thing holds good for multiplication. And then we have subtraction, division, we have signed integer division, we have modulo remainder operation, we have signed modulo remainder operation, we have modulo addition, modulo multiplication, exponential operation, and finally we have the sign extend operation, which extends the length of the 2's complement signed integer. The next category is that of comparison in bitwise logic. This has several instructions: less than, greater than, sign less than, sign greater than. The equality operator is 0, bitwise and, bitwise or, XOR, not. The byte operation, which retrieves a single byte from a word. Then we have the shift left operation. We also have a shift right operation. And finally, we have the arithmetic, which is a signed right shift operation. The next category is a single instruction, which is really critical to Ethereum, is that of the SHA-3. So this computes the Keccak 256 hash that we have talked about. And this is really the formal notation for how the SHA-Keccak 256 hash is calculated. And this is something that you will see in the yellow paper. So if you're interested in the formal semantics of how each of these instructions work, the formal notation of what is on the stack, what is in memory, and how many bits and bytes are manipulated, then I would encourage you to look at the yellow paper for these details. The next category is what is referred to as environmental information. These set of instructions give information about the environment or the execution context of the contract, of the smart contract that is executing these instructions. Let's take a look at some of these instructions. There is the address instruction, which gives the address of the currently executing account. There is balance, which gives the ether balance of the currently executing account. There is origin, which gives the address of the originator of this transaction that actually led to the execution of this code within the EVM. Then there is the caller. This gives the caller's address. In the context of Solidity, these would be transaction origin and message sender, respectively. Then there is call value, and in the context of Solidity, this would be the message value built in that you would see in the smart contracts. And then you have the 3 call data instructions: load, size, and copy that we talked about. The next instruction is code size. This gives the size of the code running in the current environment. Then you have code copy that lets you copy the code running in current environment to memory. Then you have gas price, and in the context of Solidity, you would see this as transaction.gasPrice, which gives you the price of the gas in the current environment. And then you have a set of instructions that let you query an external contract account. ext code size gives you the size of the specified account's code. Xcode copy copies the specified accounts code to memory. Then you have return data size that gives the size of the output data from the previous call in this current environment. You have the return data copy that copies that return data. And then you have Xcode hash, which gives the hash of the external accounts code. Similar to environmental information, EVM also has a set of instructions that gives information about the transactions block. It has a block hash instruction that gives the hash of one of the specified 256 most recent complete blocks. If the specified block is not one of the most recent 256 ones, then this instruction returns 0, something that has a security implication. Then there is the Coinbase instruction. This gives the block's beneficiary address, the address to which the block reward and transaction fees are credited to. There's a timestamp instruction that gets the block's timestamp. There's a number that gets the block's number. There's a block difficulty instruction and also a block gas limit instruction. The next category of instructions are related to the stack, memory, and storage, load and store operations, and also those that affect the control flow. The first instruction is the pop instruction that pops an element of the stack. Then we have mload and mstore that load and store from memory that we talked about. We also have the mstore8 that stores a single byte to memory instead of the word. And then we have the storage load and storage store instructions that load and store words from and to storage. We then have a set of instructions that affect the control flow. These are the jump that jumps to the specific location. We have a conditional jump that conditionally jumps depending on the value specified. We have a program counter instruction that gives you the value of the program counter. We have the msize instruction that gives the size of active memory in bytes as of this instruction. We have the gas instruction that gives the amount of available gas as of this instruction. And this is in the context of the gas that is supplied with the transaction, how much gets consumed and how much is left, if you recall. And finally, we have a jump test instruction. This has no effect on the machine state. It does not affect the control flow, but it marks a particular destination as being valid, as being a valid destination for the jump instructions that we talked about. The next set of instructions are specific to the stack. They are the push operations. These instructions push operands or place items onto the stack. And depending on the number of items placed, there are 32 such instructions. Push 1 pushes a single byte onto the stack. Push 2 pushes 2 bytes. And all the way to push 31 that pushes 31 bytes onto the stack. And finally, you have the push 32 instruction that pushes a full word, 32 bytes or 256 bits onto the stack. The next category of instructions that operate on the stack are the duplication operations. These duplicate items that are already on the stack. So dupe 1, for example, duplicates the first stack item. Then we have dupe 2, dupe 3, all the way to dupe 16 that duplicate those respective stack items. The final set of instructions that operate on stack items are the exchange operations. These exchange or swap the items that are already on the stack. So swap 1, for example, exchanges the first and second stack items. Swap 2 exchanges the first and third, and so on. And all the way to swap 16 that exchanges the first and 17th stack items. The next set of operations are what are referred to as the logging operations. These append log records from within the execution context of the contract onto the blockchain. We talked about this a bit in the context of the Bloom filter in the block header, but there are 5 such instructions: log 0, log 1, all the way to log 4, and these instructions differ in the number of topics that are specified as being part of the log. So the log itself refers to the event that is fired from within the context of the contract, and in the event, the different parameters can be specified as either being indexed or non-indexed. Indexed parameters go into the topics part of the log, and the non-indexed parameters go into the data part of the log. And this really differentiates how fast the parameters or the records can be queried, searched, and looked at. So these are really critical to how the contracts actually communicate some of their state to the off-chain interfaces or the off-chain monitoring tools. The next set of instructions are referred to as system operations. These include instructions that are really critical to how the system functions. They allow one to create new contract accounts, call from one account to another in different ways, revert from the current executing context, invalidate some of the things that have happened, and so on. So let's take a bit of a deeper look into each of these instructions. The first one is the create instruction. This is used to create a new contract account that has associated code and storage with it. Now recall that contract accounts can be created from an externally owned account by sending a special transaction to the 0 address, or they can also be created from other contracts when they're executed. The address of the newly created account depends on the sender's address and also the nonce of that account. So this really makes the newly created contract's address dependent on the previous transactions that have executed from the sender's account. This becomes interesting when we talk about a related instruction called create2 later on in this slide. The call instruction allows the current executing context to do a message call into another account. So now there is a caller account that is doing a message call into a callee account. So this is interesting because it lets contracts call each other in the executing context. Call code is another related call instruction. This is interesting because it lets the caller account call a callee account and let the callee account execute its code in the context of the state of the caller's account. Right? So this distinction is really critical, and it has really big security implications in some of the future instructions we'll talk about on this slide. Return instruction really halts execution and returns the output data. It's fairly straightforward. The delegate call is a very interesting instruction. This again in the call family of instructions, very similar to call code, where there is a caller account that calls into the callee account, where the callee account executes its code in the context of the caller's state. But the difference here between call code is, in the case of delegate call, the values of sender and value of the caller is used in the case of callee. So in the context of Solidity, your message sender and message value of the caller's account is used in the execution context of the callee account. This could be a bit confusing when you're thinking about it, but do take a look at one of the references provided and just work out the logic, because this is really critical to the security of a lot of the smart contracts. You will see this pattern used multiple times in various contexts when we talk about the Solidity modules as well. The next instruction is create2. So similar to create instruction that we talked about earlier, create2 is used to create new contract accounts with associated code and storage. But the difference here is that create2 allows you to create accounts with a predictable address for those accounts. So unlike create, where the address of the newly created contract account depended on the nonce, so all the transactions that happened from the sender's account, create 2 removes that so that the address of contracts being generated are very predictable. Now this has big implications again to security. We'll maybe touch upon this in some of the later modules, but do take a look. There are many fantastic references that go into the detail, the positive aspects, the new applications that create2 enables, but also some security implications or concerns with the create2 account. Static call is another instruction in the call family. This allows the callee account that is being called into to only read the state of the caller account without letting it modify. So you can imagine that this has security implications as well. The revert instruction halts the execution of the current executing context. It returns the data and it returns the remaining gas that's left behind after consuming all the gas that was supplied as part of the triggering transaction so far. The invalid instruction 0xFE is again a special instruction in EVM. It consumes all the gas that's been supplied as part of the triggering transaction, and it is used in the context of some of the static analysis tools that we'll touch upon in the later modules. The last instruction, the final instruction, 0xFF, in the EVM instruction set is a really special instruction called self-destruct. As you can imagine, this halts execution, but it also destructs the account of the executing context. This account is really registered for later deletion, and this has really big security implications because the contract account that is executing will not exist after the transaction finishes. This is something we will touch upon in some of the security aspects as when we talk about some of the findings and security pitfalls later on in the modules. So that brings us to the end of the EVM instruction set. So as you've seen, they're all very interesting instructions. All of them are single bytes. They're very different applications, different categories, systems, push and pop, things that operate on the stack, arithmetic instructions, all instructions that you could think of that could really help with the EVM stack-based architecture to keep it simple, but also let it be rich in terms of the applications that can be built using these instructions. Now let's step back and look at the gas costs of these instructions. We have talked about gas in the context of transaction, in the context of the block gas limit and so on. But where it really matters, right, the Turing complexity and the quasi-Turing completeness, the boundedness is really stemming from the gas costs that are associated with each of the different instructions that we talked about. Now, all these instructions have different gas costs, and the reason for that is because each of them has a different requirement when it comes to the computation processing power of the executing Ethereum node, let's say the miner, and also the storage requirements, the memory accesses and the disk accesses on the real physical hardware that is, that's running the Ethereum node in the context of a miner or anyone else. So when we look at the gas costs, the simplest instructions like stop, invalid, and revert that only affect the executing context in a very special way without really having a very high demand or really no demand on the processing or the storage of that executing physical hardware, the gas cost for these instructions is 0. And most of the arithmetic logic and stack instructions the gas costs vary between 3 to 5 gas units. Now let's contrast this with some of the more demanding instructions like the call family of instructions or the balance or the the Xcode hash, Xcode copy, those kinds of instructions. These have a much greater processing requirement from the Ethereum node, and these now cost 2600 gas units. And again, contrast this with the memory instructions like memory load store, which are really within the context of the EVM, very simple instructions that operate on EVM's internal data structures. These memory instructions cost only 3 gas units. However, the storage instructions like sload and store, because they deal with persistent state and because they have to access the disk or the persistent state within the physical machine of that Ethereum node, they cost much more than the memory instructions. So these instructions now, sload costs 2100 gas and store costs 20,000 gas units to set a slot, a storage slot. We'll talk about it in some of the forthcoming modules, but it costs 20,000 gas to change that storage value from 0 to a non-zero value. And there are optimizations here. This instruction costs only 5,000 gas in some of the other situations. Now, these gas costs have changed over the duration of the last 5 to 6 years as Ethereum has evolved. And these have changed to prevent some denial of service attacks that have also happened in the past. So I would encourage you to look at the yellow paper and some of the other articles that have been written around this, some of the EIPs that have been created specifically to address the gas costs of these instructions in some of the most recent upgrades like the Berlin upgrade and even some of the other upgrades to see why these costs, gas costs, were changed for some of these more demanding instructions and the rationale behind it and so on, right? So these become important because not only because they address the optimization aspect when somebody is deploying a contract, the gas usage becomes important because it affects the user experience of the user working or interfacing with these contracts. But from a security perspective, these gas costs become important from the denial of service context as well. So we will talk a bit more about this when we look at when we go to the security modules. The gas costs and why those should be low and how they could result in denial of service in different situations. The final set of instructions where gas costs are really high are really the create instruction, which is probably the most expensive instruction. It costs 32,000 gas. And as you can imagine, this is because create results in a new contract account being created. So a lot of the data structures within the EVM context are created, are registered, have to be made persistent, and so on. Self-destruct costs 5,000 gas. So very, very interesting and critical aspect of the EVM, something that's very different from the Web2 infrastructure that that don't really have this concept of gas. And we talked about this earlier because of the Turing completeness and to keep it bounded and so on. So I would encourage you to try to understand this and some of the implications as well. Reverting of transactions. A transaction can revert for different exceptional conditions. The transaction could run out of gas depending on how much was supplied as part of it and what that transaction actually needs when it is executing. The transaction could also revert because of invalid instructions that are encountered as part of executing the smart contract. So when the transaction gets reverted, all the state changes made in the context of the EVM so far, from all the previous instructions in the contract, are discarded. And the original state, before the transaction started executing, is restored. It is as if the transaction never executed from the perspective of the EVM state. So this is something very fundamental that needs to be kept in mind when we are looking at transactions, when we are analyzing smart contracts and so on. Now let's take a look at what the transaction data contains. We touched upon this when we were discussing the components of a transaction, and one of them is data. Now recall that this is really relevant when the transaction is being sent or being targeted towards a contract account, where the recipient of the transaction is a contract account. In that case, the transaction data contains two components. It has to specify the function of that contract that is being invoked, and if that function requires any arguments, then it needs to specify those as well. So this function and arguments that are the components of data have to be encoded, and this is encoded according to the ABI. And ABI stands for Application Binary Interface. Now let's take a look at what that means.